In the last session, we discussed the cadmium sulfide indium phosphide heterostructure for example 7. In this session, we discuss the overview of low-dimensional structures. Consider a geometrical size of a semiconductor of length Lx, Ly, and Lz. Depending on the system dimension, we can distinguish different cases compared with the electron de Broglie wavelength, denoted as lambda dB, which is the de Broglie wavelength. For a three-dimensional case or a bulk semiconductors, the de Broglie wavelength is less than Lx, Ly, and Lz. And the electron basically behaves like a free particle. So basically the dimension, Lx, Ly, is much greater than the de Broglie wavelength. So the semiconductor will behave like a three-dimensional case, or we call it the bulk semiconductors. Now, in two-dimensional case, which is a quantum well, that you study in Prof. Wu's course, the de Broglie wavelength is approximately equal to one of the length, let's say Lz, while Lx and Ly are still much greater than Lz. So there is a quantization of electron motion in the Lz direction, while the other two directions, the Lx and Ly direction, electrons are free to move. One-dimensional case, which is a quantum is approximately equals to Lz and also Ly direction. So only one direction, the Lx, is greater than the Ly and also greater than Lz. So there is quantization of the electron in the Ly and Lz direction, and the electron is able to move freely in the Lx direction, which is along the wire. For zero-dimensional case, or we call it the quantum box, or sometimes quantum dot, the three directions are all having the dimension of de Broglie wavelength. So the electron is quantized, or restricted in all three directions, and they cannot move freely in any of the direction. So this is a three-dimensional of a quantum well structure. So this is the dimension, the geometrical size dimension, same as this one. So it's free to move in the plane of Lx and Ly direction, but is quantized in the z direction. Now, how do we define quantum confinement? Which means that quantum confinement effect is important when we discuss semiconductors in terms of its dimension. By uncertainty, Heisenberg uncertainty principle, if we confine a particle in the region of the x-axis of length delta x, the uncertainty in its momentum is given by delta p, delta x approximately h bar over 2, where h bar is h over 2 pi and h is the Planck constant. So the momentum down here, we put a subscript x, to denote the momentum, in the x direction. If we rewrite the momentum, in terms of delta x, it will be h bar over 2 delta x. Given a free particle of mass m, the confinement in the x direction give it an additional kinetic energy of delta p squared over 2m. That is your kinetic energy, of the particle in the x direction. Or you substitute your delta p for h bar over 2 delta x, it will be of this form. Now, this confinement energy, will be significant if it's comparable or greater than the kinetic energy of the particle due to its thermal motion in the x direction. Always remember that particle always moving in random motion in the semiconductor, okay, or they are moving randomly, okay, due to thermal motion, okay, due to temperature, okay. So the thermal motion is measured by the thermal energy of kT. Now, in three-dimensional case, it will be 3 over 2 kT. For in one-dimensional case, then the kT is half kT. Okay, so equal partition. In one direction, it will half kT. Okay, three directions is 3 over 2 kT. So this kinetic energy of the particle, which is this, or this expression, if it's greater than or equals to half kT, then confinement energy is significant, which means that the confinement energy becomes important. And the quantum size effect will be important. You can rearrange the term, okay, for this equation, manipulate this equation and express in terms of delta x, it will be of this form. So it will be inversely proportional to the square root of temperature, which means that as far as we consider the geometrical size of a semiconductor, if the delta x, okay, is less than or equals to this term, then there's quantum confinement, and therefore there's a quantum size effect, which is become important. Okay, the de Broglie wavelength, okay, is given by h over px. Let's say we consider only one dimension. The kinetic energy, of course, is equals to p squared over 2m, and p is replaced by your de Broglie wavelength, h over lambda, and equals to half kT. Now, you can express lambda, okay, in terms of h over mkt. Okay, you can rearrange this term. That will give you h over square root mkt. If you compare the Broglie wavelength of 3.6 in terms of temperature and the size, the geometrical size in one direction of delta x, 3.35, we will realize that delta x can be expressed in terms of the Broglie wavelength must be less than or equals to 0.113 multiplied by the de Broglie wavelength. So it's equivalent to say that the delta x must be comparable or smaller than 0.1. Okay, let's say we approximate this to be 0.1 of lambda. Then the quantum size effect become important. Next, this is a summary of the degree of freedom and the density of state. So 3 degree of freedom is bulk semiconductors, 3-dimensional case. The density of state goes like a square root dependence, as we have discussed before. For 2 degree of freedom, okay, that is in the case of quantum well, the density of state it goes like a step function. So you have learned that in Prof. Wu's course. For a 1-dimensional case, the density of state as a function of energy goes like 1 over square root E. And for quantum dots or quantum bulks, 0 dimension, the density of state goes like a delta function. So this represents a bulk semiconductor, this represents a quantum well, and this represents a nanowire, and this represents the quantum dot or quantum box. So in terms of quantum wire, okay, you can artificially design an edge off, okay, by forming an indium gallium arsenide ridge. Then your electron basically can travel in one-dimensional case. For this case, it's basically is indium gallium arsenide. You can go on gallium arsenide. For next section, let us discuss the semiconductor quantum well. Modern growth techniques such as molecular beam epitaxy or metal organic chemical vapor deposition, it makes it possible to manufacture ultra-thin semiconductor structure of high quality. Usually, we will grow the material on a substrate, okay, or of about semiconductor. And the gallium arsenide substrate usually manufactured, okay, by the vendor is mechanical polished, okay, and often this substrate can be semi-insulating, also can be N-type or can be P-type. The very first layer that you grow on the gallium arsenide substrate, okay, is usually, okay, another layer of gallium arsenide, okay, before you grow the aluminum gallium arsenide. So the reason for growing another layer of gallium arsenide in, let's say, in the ultra high vacuum chamber is basically to smooth out any lumps or bumps of the substrate, because this substrate when you bought from the manufacturer is mechanical polished and the surface may still have some lumps and bumps. So you want to deposit another same layer as a substrate, which is gallium arsenide, to make it atomically smooth top surface before you grow the active parts of the multi-layer. So in this case, after growing gallium arsenide on gallium arsenide substrate, the buffer layer, you can grow the quantum well, which is aluminum gallium arsenide is a barrier, gallium arsenide is a well, and then aluminum gallium arsenide. Or you can grow multiple quantum well. Okay, so here you have 1, 2, 3, 4. There are 4 well. So some of these growth methods, as I mentioned, can be done by molecular beam epitaxy or using chemical vapor deposition. And most of these deposition methods, such as MBE in this case, or MOCVD, or even sputtering, as we mentioned previously, are typically far from equilibrium condition, which means they are grown in a metastable state, okay, without spinodal decomposition. Now, this shows an example of an epitaxial growth of semiconductor using molecular beam epitaxy. So these are the molecular beam epitaxy system. Your source material, okay, like for example, gallium arsenide, aluminum, okay, or even the dopant, okay, are contained in a crucible, okay, and then put in a diffusion cell. This diffusion cell is connected to some kind of heating element, okay, in order to heat up the material. So this diffusion cell are basically, you can see all around here. And this is the deposition chamber. The molecular beam epitaxial growth take place in a very ultra high vacuum chamber. The vacuum is about 10 to the minus 8 Pascal. And the deposition rate usually is about 50 nanometer per minute or about. 8 Armstrong per second, so that you allow the flame to grow exponentially. And is in ultra high vacuum, so you can achieve the same priority as other deposition technique. And these are the source itself are basically solid source. Okay, come in different granular size, can be about 1 or 2 mm of aluminum or arsenic or gallium source. Okay, and the purity could be up to 6N. Okay, N represent 9. Number of, let's say, is 99.9999. So it's 6N, 69. So that's how pure the materials, okay, that is used in the deposition system. And we use solid source, that means we don't need to involve gases. Okay, so you can able to achieve high purity of the growth film. So again, all these gallium and arsenic element or solid source, okay, in ultra pure form of 6N 99.9999 are heated in a separate diffusion cell. Okay, and then until they begin to slowly sublime. So sublimation or we say the atom sublime is a transition of a substance directly from solid to the gas phase without passing through intermediate liquid phase. And so it becomes gaseous phase, and then it travels ballistically in the ultra high vacuum, and then it reaches the wafer or the gallium arsenide substrate. So it condenses on this wafer, and then they start to react on the wafer. Okay, as they travel along this path, okay, the atoms, let's say from gallium arsenide, does not react until they reach the wafer. And behind the wafer, there's a heating element, okay, basically to heat up the wafer. So the atoms of gallium and arsenic and aluminum can react on the wafer. And because it's ultra high vacuum, all these arsenic and gas and gallium and aluminum can have a very long mean-free path. Okay, depending on the pressure and temperature that we use in the system. Long mean-free path means that the atoms can travel ballistically, okay, in the chamber to reach the wafer without interacting with each other. So all these evaporated atoms do not interact with each other in the vacuum chamber until they reach the wafer. So therefore we call this molecular beam. Okay. So quantum wells are often referred as quasi two-dimensional semiconductors because they retain some property of the 3D system, because they have limited number of quantum state exist for the motion in the z direction. Okay. In our analytical analysis, as you study in Provost course, there are infinite well or infinite potential barrier. Those are basically in the for analytical. Okay, in medical sense, there's limited number of quantum state because the potential barrier is finite. So let us look at the quantum well structure. Let's say we have aluminum gallium arsenide, gray gallium arsenide, and that aluminum gallium arsenide. This is the bundle of aluminum gallium arsenide. See, this is a regular aluminum gallium arsenide. This is type 9 metal structure. The gallium arsenide, the band gap is sandwiched between two large band gap semiconductor. The thickness, okay, of the gallium arsenide, okay, in order to have quantum size effect or quantum confinement, the length should be very small. Okay, could be in the 5 to 10 nanometer. So that form the quantum well, and you grow, let's say, in this direction, we call that the Z direction. So you flip over this from the quantum well. You can draw this in three-dimensional case. So once you flip over, the Z direction is in this direction. So the quantum size effect or the quantum confinement or the quantized level is in the Z direction. And the XY direction, okay, the plane of XY, the electron is still free to move. So the XY plane will be the plane, okay, down here. And this is the Z direction, okay? So the XY plane is basically the surface of the semiconductors, okay, of the gallium arsenide or the aluminum gallium arsenide, okay, along the plane of the semiconductors. Now, we have discussed, okay, previously that this is the conduction band offset, and this is the valence band offset for aluminum gallium arsenide and gallium arsenide quantum well. And these are the quantized state. N equals to 1, N equals to 2, N equals to 3. And this is the electronic energy of the quantized level measured from the bottom of the conduction band. So h bar squared, pi squared, n squared, or j squared, j equals to 1 over 2 MEL squared. Okay, and similarly for the whole, okay, measure from the top valence band, h bar squared, pi squared, j equals to 1, 2 MHL squared, where M is the whole effective mass. Next, there is a selection rule for the transition of the electron, okay, from the valence band to the conduction band for a quantum well. So if you come in with a photon energy, the electron can absorb photon energy by going from n equals to 1 to n equals to 1, or n equals to 2 to n equals to 2, or n equals to 3 to n equals to 3. Okay, the selection rule does not allow for you to go from n equals to 1 to n equals to 2. Okay, so the change, okay, in n is basically 0. N equals to 1, n equals to 1, the change is in n is 0. Okay, this arrived from the quantum mechanics, which we shall not dealt with in any details here. So we take the result that the optical transition, okay, is from n equals to 1, n equals to 2 to n equals to 2, n equals to 3 to n equals to 3. That is the selection rule for the optical transition. Again, for type 1 quantum well, this delta Eg is a change in band gap, delta Ec is of this value, and the energy, quantized energy, is of this expression, assuming that we use infinite well approximation, which means because in practical devices, the well is basically finite, or the potential barrier is finite, which is delta Ec. Okay, for our analytical calculation, okay, we'll assume this well is infinite. So you can use this expression. Now, I do not want to go into details, Okay, to talk about electronic state for the infinite potential barrier in solving the Schrodinger equation, or the finite potential barrier, which is in this case finite well. You have studied that in Prof. Wu's course. So I just need to summarize, okay, the essential result. So for a infinite potential barrier, okay, that means the barrier is infinite or the well is infinite, okay, you have infinite quantized level, okay, and this is your well width. So again, for the xy motion, which is free to move, your electron energy in the conduction band is h bar squared over 2 me star, the electron effective mass, k squared plus ky squared. Okay, for the hole, the same thing. So this, you can write it as the E perpendicular, which is in the xy plane. So, and then you can combine the electron energy plus the hole energy to become the reduced mass and k squared plus ky squared. So the carrier is free to move in the xy plane, and the corresponding energy band is parabolic because it goes like a polynomial of degree 2. For the z motion, which is the quantized direction, okay, the energy is h bar squared to mj squared pi squared over l squared, where j is your integer, or sometimes we call that the quantum number. To sum up the contribution in the xy plane and the z direction, the total energy of the electron and hole can be expressed in this form. For electronic state of a finite potential barrier or a finite well, which means that the well is finite. So your quantized level, okay, is finite. Okay. Beyond the potential barrier height, okay, there's no more quantized level. So it's a finite potential barrier. So you can solve your Schrodinger equation, okay, for the finite potential barrier. So electron in the finite quantum well, when you solve the Schrodinger equation, the solution to find the energy is obtained either, it can be obtained graphically. This is Prof. Wu's course. So the intercept here you can find the energy value. Okay, so we can solve the equation graphically to obtain the eigenvalue, which is either the k or the eigenvalue or eigenenergy. Okay, eigenvalue is a wave function, eigenenergy is your electron energy. So this, in these slides, okay, I took it from Prof. Wu's course for a finite potential barrier, or we say a finite well. Okay, your electron energy can be obtained graphically. For an infinite potential barrier, this will be your equation. Okay, j squared pi squared over lz squared, which we can solve analytically. Otherwise, you solve graphically for the finite potential barrier, or you solve it analytically. Now, I just want to point out that in these slides, that in Prof. Wu's course, the m itself, the mass, okay, the effective mass is assumed to be the same for both barrier and the well. Now, the revised slides, okay, in practical sense for semiconductors, the barrier and the well are of different material. The well is gallium arsenide. The barrier is aluminum gallium arsenide. So you expect the effective mass for the well and the barrier to be different. So the M will have to be distinguished between the barrier and the well. So MB is the effective mass of the barrier, and NW here is the effective mass of the well. When you solve the equation graphically, eventually you have to obtain the electron energy, okay, in terms of the effective mass of the well. Okay, and the kx itself, okay, you have to find for the intercept of these two curves. So this diagram again shows a finite potential barrier, and the quantized level, there are only 4 quantized level. Okay, this one show only 2 quantized level. Okay, very much depends on how large is the potential barrier height, okay, or the conduction band offset. So for this, okay, we see that the potential energy V naught, okay, which is also your delta EC, your conduction band offset, measure from here to here, okay. If it's lower, okay, than V naught, then your quantized energy at the 4th level, okay, may not be quantized. So it become unbound and you merge with the continuum. Okay, similarly, as you keep lowering your V naught, you may not have a quantized level of Ez. Okay, so in this case, you have only 2 quantized level. So the quantized bound state energy vary like a 1 over Lz squared. Okay, so let's say in the case of infinite square potential, energy is proportional to the well width Lz squared. As your Lz or the well width decreases, your bound state energy shift to higher value. So imagine this is your quantized state, okay, at n equals to 1. As you decrease the well width, this state will push up. Okay, so it shift to a higher energy. So this shift to a higher energy, we call that the blue shift again, because it shift to a higher energy or shorter wavelength. Okay, due to the quantum confinement effect, we call this the quantum size effect. Let us look at the quantum size effect by changing the size of the quantum well. Okay, this is a photoluminescence emission, okay, of the quantum well, or you can see also as an absorption. Now, this is the well width is of 9 nanometer. So this is the transition energy, corresponds to this peak A. Okay, as you reduce the size to 6 nanometer, this level will push up. Okay, this level will push down because your energy is proportional to Lz squared. As L reduce, energy increases. So the same quantized level, let's say n equals to 1, you will be at this level. Okay, and J equals to 1 in the whole, in the valence band, you will push down. So this is the emission, okay, due to this transition energy. So it's at a shorter wavelength, so higher photon energy. As you decreases your size, let's say to 4 nanometer, okay, original will be at this level, you push up into a higher level. And this also push now to a higher level. So the whole transition energy, okay, will be higher. So that corresponds to the emission for C, okay, at the higher photon energy or shorter wavelength. As you reduce further, okay, to 4 to 2 nanometer, from 4 to 2 nanometer, your transition energy again, okay, will be higher. That corresponds to D. Okay. As you going to reduce further, okay, to 2 nanometer to a smaller value, which means that your well width tends to 0, which means there's no well width, then the whole quantum well will recover to become a bulk semiconductor. So there's a limit to the size of the well width you can reduce. Okay, so if you L tends to 0, okay, then you are basically become a bulk semiconductor, and there's no quantum size effect. Okay, the semiconductor doesn't behave like a quantum well. Now, as you decrease your well width, you can see that actually your signal start to decrease. Okay, some of this decrease in signal can be due to the defect. Okay, as you approach some kind of critical thickness of the well width, as your well width gets smaller, there could be increase in the non-radiative recombination rate. Okay, so the quantum efficiency could decrease. So it's not easy to grow uh, very small size of quantum well or small well width. Now, for infinite square potential approximation, because as we say in practical sense, the well is finite, the barrier potential is finite. So if we want to use the infinite square well equation, then we are basically saying that we are using infinite well potential as an approximation to calculate your finite well potential. Just to be clear about the notation, okay, in certain textbook, the quantum size energy sometimes is written in this form, sometimes it's written in this form. If it's in this form, there is j plus 1, but the j will start from 0. Okay. In this form, the j will start from 1. So when j goes to 1, and for this case j goes to 0, they have the same equation or same value. Okay. So let us stick to equation 3.4.5a in our course. And the usual terminology that we use is when j equals to 1, we call that the ground state energy, which is the lowest state quantized energy. When j equals to 2, we actually call it the first excited state energy. And j equals to 3 is the second excited state energy. Okay? Or instead calling it excited state energy, sometimes we call it the quantized energy. Or to be exact, if it's in the conduction band, we say that it's a quantized electronic state energy. So to be clear, J equals to 1 is the lower electronic state energy in the conduction band, and we call that the ground state energy. So as I mentioned, in practical sense, quantum well have a finite potential barrier. But however, we will try to use infinite well approximation to calculate the quantized energy level. Because for finite potential barrier, you have to calculate either by numerical means or by graphical means. But sometimes we can use an infinite well approximation to calculate the quantized energy, which is of this equation. So when is infinite well approximation a good approximation? When the first electronic state is much, much less than delta EC. Or similarly, the first or lowest electronic whole state is much, much less than delta EV. To put it in another words, when is infinite well approximation a poor approximation? If your well width is very small, okay, or your delta EC or delta EV is very small. Let us look at the quantized electron energy. Okay, it's a function of wavelength. Okay, let us take the quantized electron energy, okay, for the lowest electronic energy, okay, which is J equals to 1. Okay, J equals to 1, which is the lowest energy. Okay, let us take this value as an example. Now, this is a plot, okay, of the E1, which is the lowest electronic quantized energy, okay, in a quantum well as a function of wavelength. And there are two curves here, okay. The lowest electronic energy is calculated by infinite well, which is a dashed line, and the other one is by the finite well, which is by graphical mean. And let's say the finite potential, which is delta EC, okay, is about 250 MeV, okay, for this case, okay, for finite well. So for very large well width, okay, you can see about 30 nanometer. The two curves almost coincide. So for very large well width, the semiconductor, this material, which we try to design as a quantum well, may not have quantum size effect. Okay, you can see that the E1, the electron energy, is almost zero. There's no quantum size effect, and there's no quantized electronic energy level, which means that it behaves like about semiconductors. And you start to decrease the wealth, okay, less than 30 nanometer. Let's say you go to 15 nanometer, then you can see that the electron energy, okay, will have start to have finite value. And compared to finite well and infinite well in calculating your electronic energy, you can see the electronic energy in the finite potential, the solid curve, okay, is always less than that in the finite well approximation. So if you use an infinite well, okay, to calculate electron energy, okay, you realize that it will be always larger than the finite well, okay, calculation for your electron energy. Now, and they start to deviate apart as you go into smaller well width. Okay, it will become very prominent. Okay, the electron energy in the finite well is always less than the infinite well approximation when you calculate electron energy. Now, in the extreme case that you go to very small L, okay, where your electron energy is almost equals to the potential barrier height, which means that this energy goes all the way up to here, almost your delta EC. Okay, this makes the electron just slightly confined in the quantum well. Now, and of course, as you go to even smaller well width, L tends to 0, there's no well width, which means that the quantum well recover like a three-dimensional case. Because at the end of the day, you're pushing this state, okay, above the potential barrier height. There's no more confinement effect. Because you can see that for 9642 nanometer, your first electronic state, the lowest electron, keep pushing up. And if you go even smaller than 2 nanometer, this state may not be confined. It may be in the continuum. Okay. So therefore, it will recover like about semiconductors. Now, let us further distinguish, okay, in terms of the wave function and the electronic energy, okay, in the quantum well for single quantum well and multiple quantum well. For an infinite well, okay, the wave function does not penetrate outside the well. You can see that the wave function all confined in the well, okay, and the electronic state, which is a discrete state, okay, discrete subband, okay, is infinite because this goes infinite. Now, for a finite single quantum well, the wave function actually penetrate outside the well, okay, and the discrete subband, of course, is finite depending on the potential barrier height. If you grow multiple quantum well, that means more than one quantum well, sometimes two well, we call a double quantum well. So more than two is we call a multiple quantum well. Again, okay, you go similar well, discrete subband, okay, quantized energy level, wave function penetrate into the well, but this wave function, okay, does not overlap with each other. Okay, when it penetrate here and this penetrate here, it does not overlap with each other. That is for multiple quantum well. Now, if you grow the well such that the barrier width, this is known as the well width inside the well. Okay, this is known as the barrier width. If it's thin enough, then this wave function will overlap with each other. So in this case, okay, if your barrier width, which is B, okay, down here, is thin enough, then the well with the wave function penetrate outside the well will overlap with each other. Once we overlap, so the well is so close that the wave function will couple to each other. Okay, once wave function couple to each other, it will give rise to band, and we call this the mini band. Okay, so the discrete energy now broaden into band, and such a device, okay, we no longer call it a multiple quantum well, we call it a superlattice. Okay, so this is another branch of semiconductor physics, okay, which we do not want to delve into this course because of the time limitation. Now, to summarize, figure 3.4.10, this figure, okay, I think I made a mistake, 3.4.10, okay, and 3.4.11, infinite well, electron wave function is confined in the well, doesn't penetrate into the barrier. Finite well, electron wave function penetrate into the well. Let's say there are two or more well, the wave function does not overlap with the electron wave function in the other well. Now for superlattice, the barrier width is thin enough such that the electron wave function overlap with the adjacent well. Okay, there's a wrong spelling here. WIDTH, that's the width. Now in infinite well potential, the quantized energy are greater than the finite well. Okay, I think there's a mistake here. Should be greater than that in the finite well. So it's in this case. Okay, the quantized energy, okay, for infinite well is greater than the finite well. Okay, for the is greater than finite well. The quantized energy in the finite well is reduced as compared to the infinite well. And also the separation between the energy level is also reduced. For the superlattice, the neighboring well interact. So they basically, the quantized energy, they broaden into band, called the mini band. So electron can move inside the mini band. For infinite well potential, number of confined state is infinite because the barrier is infinite. And of course, obviously, finite well potential, the number of confined state is finite. Now, density of state in three-dimensional case, two-dimensional case, and one-dimensional case, okay, have been discussed in Prof of course. So I do not want to go into the details again, but basically 3D case grows like a square root dependence, okay, of the energy. 2D is a step function. Okay, 1D, okay, goes like 1 over square root E. And this is a density of state in two-dimensional case. I bring up this slide of Prof course because I want to make use of the density of state in 2D case since we are talking about the quantum well. So this function here is a step function. Okay, let us discuss more of it later as we see an example how to calculate the density of state. Okay, again, three-dimensional case goes like a square root dependence. Okay. And then 2D case step function. Okay. So the step function, the density of state, okay, will be measured, okay, in terms of m star over pi h bar squared. Okay. And 2m star pi h bar squared and 3m star pi h bar squared over pi h bar squared. Okay, step function. Okay, let us look at as an example. How do we calculate the electronic state in the conduction band of bulk gallium arsenide? So in this case, let us calculate three-dimensional case. Okay, between energy 1.0 eV and 1. Measured from the size of the gallium arsenide is 10 micron cube. So if all these electronic state will occupy with electron, what will be the electron density? So if we look at three-dimensional case, okay, let us draw in a spatial energy diagram. You measure from the bottom conduction band, the electron is 1 eV. Okay, measure from the bottom conduction band, the other is 1.1 eV. Again, the number of state, okay, is the volume times the density of state. So you integrate from EC plus 1.0 to EC plus 1.1. And then you can do your integration. You will get, you substitute your density of state in this for GE, the density of state equation. The volume is here. So you can plug in all the value, volume, okay, the size, effective mass, let's say in gallium arsenide, okay, is 0.067 m naught. And then you integrate from 1 to 1.1. In the integration, after integration, your EC will cancel off. So you will get, okay, 1.2 times 10 to the power of 8 electronic state. Okay. Example 9. Consider a semiconductor quantum well of aluminum gallium arsenide, aluminum gallium arsenide. So the gallium arsenide is a well, aluminum gallium arsenide is a barrier. So we use infinite well potential approximation. Calculate the first quantized energy level in the conduction band. Okay, assuming the width of the gallium arsenide 50 Armstrong and the area is 10 to the power minus 4 cm squared. What's the effective mass and whole effective mass given to you? Calculate and plot the number of states corresponding to the 4 quantized energy level. Calculate in part A. So, infinite well approximation is this equation. Effective mass in the conduction band 0.06 multiply the free electron mass. The well width is 50 Armstrong, 50 times 10 to the power minus 10. Okay, J squared, J will range from 1 to 4 for our case. Okay, when you calculate this, it will be in joules. Divided by 1.6 times 10 to the power 19, that will give you in EV. So you substitute J to be 1, 2, 3, 4, you will get this electronic quantized energy. Now the number of state, okay, is the density of state times the area. So the density of state will be ME star over pi h bar squared times the area. Area is given to you, effective mass given to you. H bar squared, you can calculate. That give you 1.75 times 10 to the power of 28 per joules. And you convert that to per EV. So if you plot the number of state as a function of electron quantized energy, okay, then you have E1, E2, E3, E4 down here. E1, E2, E3, E4. So it will be a step function. So this first, now the first from E1 to E2, the number of state will be 1 times 10, 1 times 2.8 times 10 to the power of 9. And then it jump up, okay? So this from E2 to E3 will be 2 times 10, 2 times 2.8 times 10 to the power of 9. Okay, that is the state. And then from E3 to E4, okay, you jump up, this will be, okay, 3 times 2.8 times 10 to the power of 9. Okay, number of state. So that's how you count the number of state, and therefore this is a step function. Remember that the total energy of the particle, okay, in the infinite potential barrier, okay, you have the kx, ky direction, which is known as the k perpendicular direction, and then you have the z direction, which is the quantized energy. So this is your quantum well again, okay. This is a wave function and does not penetrate outside the well. And this is in the k perpendicular direction, okay. Energy as a function of k, ks squared plus ky squared. So it's a parabolic band, okay. And this is the density also as a function of energy, again, the step function. So in the kx, ky direction, as a function of energy in 3-dimensional plot, okay, you will look like this. Okay, this is based on numerical simulation. So you have a 3-dimensional plot, okay, in this form for the kx, ky direction. So basically for each of these parabolic band, you have a constant density of state. Okay. So the density of state is actually given by a step function. Okay. So that summarizes, okay, the wave function of an infinite square potential and the energy in the 2-dimensional, okay, and then the density of state in the for the step function, okay, in the quantum well. Next, Let us discuss the exciton in two dimensions. Now, we have previously discussed the exciton in three-dimensional case, which is bulk semiconductor, due to the Coulomb attraction between a free electron in the conduction band and free hole in the valence band. Similarly, you also have exciton in the quantum well, which is two-dimensional. And we solved the Schrödinger equation for 3D, so we need to solve the Schrödinger equation for exciton in 2D. The only difference is you need to add the confinement potential, which is the delta EC plus delta EV. And that is your V naught, okay, which is your potential in the conduction band. So that equals to delta EC plus delta EV. The potential for the conduction plus the potential in the valence band. That is delta EC plus delta EV. So I do not want to go into solving the Schrödinger equation, but I will just quote you the result. So the solution for the relative motion in the xy plane will give you the band gap plus the quantized energy minus the exciton binding energy. Of course, will depends on n. Okay. So for a binding energy in the 3D case, we rewrite the equation down here again, which is of this form. You can check 2.7.12. Okay, that is the 3D binding energy. So this epsilon B is the binding energy for bulk semiconductor, which is a three-dimensional case. Now, the second term down, this is the quantized energy. Okay. Now, the third term is the Coulomb interaction between the exciton and the conduction band and the hole in the valence band. And that gives you the 2D exciton binding energy. The 2D exciton binding energy is expressed in terms of 3D binding energy exciton value. And for n equals to 1, so 1 minus half goes like a squared. Okay, and then that will give you 1/4 squared divided by 1/4 squared. That will give you 4 times the binding energy in the 3D case. So essentially, okay, the binding energy for the exciton in two-dimensional case is basically 4 times the binding energy of the exciton in three-dimensional case. Now, for the ball radius, okay, exciton in two-dimensional case, okay, the ball radius can be expressed, okay, through the binding energy in two-dimensional case. So the binding energy, okay, for 2D can be expressed in terms of the exciton ball radius in two-dimensional case. Now, the ball radius of the exciton in two-dimensional case can be expressed in terms of three-dimensional case. It's basically half of the three-dimensional ball radius, okay, of the exciton. So the ball radius of the exciton in two-dimensional case is only half of the ball radius of the three-dimensional case. Remember the ball radius, okay, is of this form. So that is your bulk semiconductor. So it's only half of the value of the 3D value. So imagine in bulk gallium arsenide, okay, your binding energy is 4.7 MeV that we have calculated before. The ball radius in 3D case is 120 Armstrong. So in quantum well, it becomes 60 Armstrong. So this exciton and bulk gallium arsenide, of course, is, let's say, is free to move. Okay, it's about 120 Armstrong in terms of its dimension. So, and then let's say you reduced, okay, in the ball radius is reduced by half in the quantum well. So it's like being squashed between the two well. So the size is being reduced. Now, in quantum well, the well width, okay, is usually much smaller than the ball radius in three-dimensional case. So, if that is the case, then quantum confinement is important, especially in the limit where the well width is much smaller than the ball radius, okay, of the three-dimensional case. Then the exciton will have a property of a two-dimensional hydrogen atom, which means that in the quantum well, you are bringing the electron and hole much closer together in 2D compared to 3D, because you have the well wall, okay, the well, okay, the exciton inside the well, okay, is squashed by the two wall, okay, so that is your potential barrier. So therefore, you're bringing the electron and hole closer together. So the exciton binding energy will have to be enhanced. You're closer together, Coulomb attraction energy is higher. So the exciton binding energy in the three-dimensional case, in the two-dimensional case, will be 4 times that in the three-dimensional case. So let us look at one example. Gallium nitride arsenide quantum well. So assuming this is the well material, and the well width is much smaller than the 3D exciton ball radius, calculate the exciton binding energy. Okay. First, in order to calculate the exciton binding energy, basically, we need to calculate the exciton binding energy in 3D case, and then we multiply by 4 times. And the binding energy for 3D case, okay, you need to calculate the reduced mass, okay, the dielectric constant. Okay. So for alloy, you have to do linear approximation to calculate the reduced mass of this material. Okay, so by linear approximation, okay, gallium arsenide 0.8 over the electron effective mass, and then 0.2, which is the gallium nitride, which is the 0.09, which is the effective mass of gallium nitride. Okay, and then you get the effective mass of the alloyed gallium nitride arsenide. Similarly, you do that for hole, and then you calculate the reduced mass. The dielectric constant for gallium nitride is 8, gallium arsenide is 13. You also can do a linear approximation. So basically, 8 times gallium nitride times 8 times 0.2 plus 13 times 0.8. Okay, that is the linear extrapolation. 3D exciton binding energy, reduced mass calculated, dielectric constant calculated. Okay, you get 6.4 MeV. So for ground state 2D, you just need to multiply by 4. Okay, and that gives you 25.6 MeV. So the exciton in two-dimensional case is almost, okay, able to observe, okay, at room temperature, which is 25.6 MeV for KT, okay, at around room temperature. If you would, for 3D case, 6.4 MeV, you can't see acetone, okay, for gallium nitride arsenide as an alloy, okay, at room temperature. But you use it as a quantum well, the binding energy is 4 times. Therefore, you are able to see, almost able to see the acetone effect in two-dimensional case, okay, for quantum well. Okay, for this course, we don't need to worry about n, okay, greater than 1. So we just take n equals to 1. That is the ground state, and that is the to calculate the binding energy of the two-dimensional case for quantum well. Next, optical absorption. This summarizes the optical absorption, okay, for 3D and 2D. So in optical absorption, okay, absorption coefficient as a function of photon energy. Absorption coefficient as a function of photon energy. The absorption coefficient goes like a square root dependence. Okay, high purity semiconductors. There's no, without acetone, it will go like square root dependence. With acetone, there will be a sharp peak, okay, riding on top of the square root dependent curve. So there's a sharp peak, and that is the acetone effect. For the density of state, three-dimensional case, the density of state goes like a square root dependent again. The density of state in two-dimensional case, okay, will be like a step function. So this is the case for the absorption coefficient, okay, especially when there's no acetone effect. So if we have acetone effect for a quantum well, you expect to see peaks, okay, riding on top of this step function. Okay, that is the optical absorption in two-dimensional case. We shall see this in the some of the experimental result. Next, let us discuss an example of aluminum gallium arsenide quantum well. So this is the aluminum gallium arsenide, and this is the gallium arsenide band gap. So these are the quantized energy. So assuming we use infinite square potential, this is a plot of the optical transition energy as a function of the well width, or the quantum well thickness. And these two curves is measured at different temperature. So the optical transition energy, okay, similarly for absorption, n goes to 1 to n goes to 1. So if you absorb my energy, you excite the electron, okay, from here to here, you leave a hole behind, and if the electron and hole recombine, you give up this photon energy. Okay, so this is the optical transition energy. So the optical transition energy will be the first lowest electron energy plus the band gap plus the lowest hole energy. Okay, so that the lowest transition energy will be 1E plus 1H plus the band gap of gallium arsenide. Okay, if you want the first excited state transition energy, you can go from here, n equals to 2 to n equals to 2. Then you have 2E, 2H, okay, and then plus the band gap energy. Now, you can see that, okay, the temperature at 2 Kelvin, the optical transition energy for this case, okay, let's say we take only the lowest electronic energy transition to the lowest hole energy, okay. Temperature at 2 Kelvin, this curve is always higher than this curve. The reason is because, okay, the band gap, remember, is temperature dependent. So this band gap, as you go to lower temperature, of course, that will contribute to your transition energy. That causes the curve for the optical transition energy measured at 2 Kelvin to be higher than that of the curve measured at 300 Kelvin, because the band gap at low temperature is 1.512 for gallium arsenide, and band gap at 300 Kelvin is 1.42. And then as the well wave start to decrease, the optical energy basically start to, okay, increase quite drastically. Okay, and the reason is also because your energy, okay, if you use infinite square potential approximation, the energy goes like 1 over L squared. So therefore, you expect to have this increase. Okay, in terms of 1 over L squared dependence. Now, the cross, the star, and also the square symbol are basically due to the composition of the aluminum in the aluminum gallium arsenide. Okay, the X itself, the X value down here. Okay, you change your aluminum composition, you change the band gap of aluminum gallium arsenide. Therefore, if you change this band gap, of course, you're going to change your delta EC. Okay. But however, let us discuss only the first electronic transition energy. So it goes like as the well thickness decreases, the optical transition energy decreases. Okay. Another example for the circulant germanium quantum well, what is the absorption age for a quantum well? We talk about absorption age in three-dimensional case. So for absorption age in quantum well, that is the lowest absorption that can occur in the quantum well, which means that it goes from J equals to 1 to J equals to 1. So you're able to calculate the electronic energy, the whole energy of the quantized level plus the band gap. Okay, you will get the absorption age in the quantum well. Again, we assume infinite square well approximation. Okay, I will leave this example to you. Okay, talking about aluminum nitride as a barrier, indium gallium nitride as a well. Okay, and then you calculate the minimum absorption required to make a transition from J equals to 2 to J equals to 2 instead of J equals to 1 to J equals to 1. Okay, using infinite barrier height, or sometimes we call that the infinite well approximation. So these are the calculation. Okay, we can go through that and also calculate the binding energy in the quantum well, which is 4 times that of the binding energy of the in the three-dimensional case. Next, let's talk about the multiple quantum well. Usually, you have single well, you have two well, we call it double well. More than two well, we have so-called the multiple quantum well. Okay, the advantage of using multiple quantum well compared to a single quantum well is because your carrier need to be trapped in the well. So there's a reasonably high probability that if you use a single quantum well, your injected carrier may not be able to trap in the well, and then it would just transit. Okay, particularly as the well width decreases. If you have many wells, then the probability of the carrier captured in the well, okay, or the hole being captured, okay, in the well, there will be high chance that the carrier being collected in the well, okay, because your cross-sectional area of your carrier, okay, in the well will be larger than the number of well present. So you're more carrier able to trap into the well as compared to a single quantum well. So again, gallium arsenide from the well with thickness or well width, okay, of LQW, and then the carrier is confined. Okay, the wave function again, it will penetrate into the barrier for practical real devices, but they do not overlap. The wave function does not overlap with each other. And for aluminum gallium arsenide quantum well, the band gap usually is about 1.79 EV for composition of 30% aluminum. Conduction band about 0.25. Valence band about 0.12. All these can be measured experimentally. Gallium arsenide 1.42. Okay, assuming all these we measure at the room temperature. Now, again, in bulk gallium arsenide, remember at the valence band, okay, this is the profile diagram. The top of valence band is 4,4 degenerate because the heavy hole and the light hole all occur at the zone center at K equals 0. Okay, so it's 4,4 degenerate because remember of the electron spin. The electron can spin up and spin down for each band. So therefore, your heavy hole and light hole, so therefore is doubly degenerate, or sometimes we call that 4,4 degenerate. Okay, because electron can spin up and spin down for each band. So each band is doubly degenerate. So if a heavy hole and light hole at this point, then is we won't call it double degenerate, then we call it 4,4 degenerate. Okay. Similarly for split off band, it was electron spin up and spin down. So it's also doubly degenerate. Now, for in a quantum well, okay, because we artificially design the well, so we consider the quantum confinement effect or the quantum potential is like a perturbation. It perturbs the system because we artificially design the system. And therefore, at this top of the band, where the energy is 4,4 degenerate, this degeneracy can be removed, or sometimes we call lifted, due to the quantum confinement effect. So instead of heavy hole and light hole, okay, merged and occur at this point, it can be removed, or we call it lifted, so it can split into a heavy hole and light hole. Okay, instead of J equals to 1, you just draw one subband. You can draw two subband, okay, due to heavy hole and light hole. So for J equals to 1, you can heavy hole and light hole. J equals to 2, you also can have a heavy hole and light hole. So the transition now, okay, again, is still from J equals to 1 to J equals to 1, but one is due to the heavy hole and one is due to the light hole. And this can be observed experimentally. So let us look at the absorption experiment, okay, measured at 2 Kelvin of the aluminum gallium arsenide and gallium arsenide. Okay, so absorption coefficient as a function of photon energy. This is measured in MeV. So this 1,500 MeV is 1.5 eV. For a 4,000 Armstrong well width, so this will behave like a 3D bulk gallium arsenide. Because the well width is so large, there's no quantum confinement effect. Okay, so you just see a very strong exciton peak, just like in bulk gallium arsenide. Now, as you reduce the well width to 210 and 14 Armstrong, 140 Armstrong, which is 21 nanometer and 40 nanometer, you can start to see exciton peak, okay, due to this transition. J equals to 1 to J equals to 1, J equals to 2 to J equals to 2, J equals to 3 to J equals to 3, J equals to 4 to J equals to 4. So this is the exciton peak due to the bulk semiconductor. Next is the 210 Armstrong well width. Okay, that is E1. Now, as you go to 140 Armstrong, because the confinement effect is so strong, we did mention that, okay, the degeneracy can be lifted. So it can split into heavy band, heavy hole, and light hole. So you can have heavy hole and light hole transition, okay, down here, heavy hole and light hole. It's not easy to see, but you can see the peak compared to 210 and 140. The transition itself, okay, the peak itself is a bit asymmetrical. Okay, it can be resolved into heavy hole and light hole transition. So for 210, you have E1, E2. Okay, again, for 140, you have E2, but the heavy band and light hole band can be actually resolved. And furthermore, remember that as you go to a smaller well width, your transition energy shifted to higher photon energy. So E1 is higher than E2. Okay, E1 in 140 Armstrong is higher than E1 in 210 Armstrong, and E2, okay, in 140 Armstrong is higher than 210 Armstrong. Okay, so on and so forth. All the peaks shift to higher photon energy. So this peak actually is asymmetrical. It can be resolved to heavy hole and light hole. Okay. Now, if you look at this part, okay, this part is pretty flat. So I'm drawing it like a density of state. Now, the reason is because the detector, unfortunately, when you used at that time during for this experiment, it did not give a very good flat response. So the step in the absorption cannot be seen clearly. But the pair of the strong transition between the heavy hole and light hole can still be resolved. Okay. So I did mention, okay, in the previous diagram, okay, this is the step absorption. If you have exciton, you'll be riding on top of it. So you can see that exciton, peak, flat, exciton, and then flat, and then acetone, and then you go flat, and then acetone peak. So in this experiment, actually the step function is not so well clearly seen because the detector used did not give a very flat response at that time. And this is measured at 2 Kelvin. Now, as the technology improved in terms of detectors and also the high quality film can be deposited due to the improvement in the growth chamber. Okay, you can even measure absorption right now as a function of photon energy for aluminum gallium arsenide at room temperature, 300 Kelvin, compared to 2 Kelvin. And we can even grow well width of 100 Armstrong, even smaller than 140 Armstrong. And you can see that, okay, the heavy hole and light hole can well be resolved compared to this one. Okay. Now, all what I have mentioned is being described down here. Now, the other important point is about the line width. Okay. Remember, in photoluminescence, the peak itself have a line width, which we call the full width half maximum. So this width, okay, is the line width, the full width at half maximum. Now, the full width half maximum of the acetone peak in multiple quantum well, okay, are broader than those of the bulk material. You can see that this well width compared to the bulk semiconductor, the well width is much larger. As you grow smaller well width, okay, as you grow smaller well size, okay, the well width will get broader. Okay, such a well width actually, okay, the broadening of this well width is due to the fluctuation in the well size. So during the growth processes, your well size may not be able to keep absolutely constant. Okay, if you grow multiple quantum well, okay, every well you need to be precise to keep at, let's say, 100 Armstrong. And such a well size, okay, during the whole grow process, maybe grow for 1 hour. For each well, the well size or the well width cannot be kept absolutely constant. So therefore, there's a fluctuation in the well size. Okay, so you may lead to a quantum well with smaller thickness fluctuation, and therefore the well size or the well width, okay, plus minus a delta L, that give you some error bar. And this fluctuation in the well size will be reflected as a broadening in the well width. Okay, so you will not expect to be a sharp peak, but there's due to this broadening effect, okay, due to the well size fluctuation. And other broadening effect could be due to the interface roughness. When you grow the material, the interface will not be so smooth, or there's a fluctuation in the alloy composition. So instead of aluminum 30%, you grow aluminum gallium arsenide for the barrier, there may be some fluctuation in the aluminum, maybe 30 or 30.05. So that all add up to the broadening of the well width. I mean the broadening of the peak itself, the acetone peak. Okay, so all this broadening can be due to the well width fluctuation, or we call that the well size fluctuation. Okay, could be due to interface roughness. It could be due to alloy composition. So all this add up to the broadening of the well width. Okay. Of course, there are also broadening effect in the bulk semiconductors because, again, your electron will collide with your lattice, and that also contribute to the broadening effect of the acetone peak. Okay, whereas your acetone move inside a semiconductor, it will collide with your lattice vibration or colliding with the phonon. So that will add to the broadening of the bulk semiconductor. Okay, but compared to the quantum well, in quantum well, the broadening, okay, could be due to many other effects. Okay, could be interface roughness, alloy composition, fluctuation in the well size. This shows the absorption spectra of a multiple quantum well measured at 6 Kelvin and 300 Kelvin. So this, you can see the thickness of the well size or the well width is 7.6 nanometer, even smaller, 76 Armstrong. Okay, this one is 10 nanometer, about 100 Armstrong. Measure at room temperature. We measure at 6 Kelvin. Okay, you can see that, okay, for n equals to 1, the heavy hole and light hole can be split. N equals to 2, the heavy hole and light hole also can be split. And n equals to 3, the heavy hole and light hole can be split. Okay, and similarly, heavy hole and light hole can be split for a thickness of 10 nanometer. Okay, and then this n equals to 2. May not be able to resolve. Okay. We will stop here, and our next section, we will talk about inter-subband transition, which is transition only in the conduction band or only in the valence band. And such a inter-subband transition can be used in quantum well infrared photodetector.